and welcome to today's lesson. I'm Mrs. Miller. Today, we will explore the question, how do light rail trains start moving? Are you ready? Grab your pencil and your science journal, and let's get started. How do you think the number of people on a train affects its motion? I don't think a few people would affect the motion, but when the train is full of people, do you think it is harder for the train to start moving? I wonder whether the number of people on a train can affect the motion of the train. Maybe a train full of people takes more force to move than an empty train. I wonder if a train's motion would be affected when the train is crowded with people. How can we test whether mass affects the motion of a train? Maybe we could use the train model again. This time, we could change the train model's mass. We could push one empty train model and one full train model and see how fast they go. I think we're ready for another investigation. Today, we will try to answer the question, how does a train's mass affect how the train responds to forces? We learned that stronger forces can cause objects to move faster than weaker forces can. Do you remember how we learned this? We learned this from our investigation. Let's look at the data from our last lesson. In our last lesson, the variable we tested was force. What is the variable in this investigation? The variable in this investigation is mass. Today, we will repeat our trials for a 4-Newton force. But this time, we will test our train models at different masses. How can we change the mass of the train model? Maybe we could put something inside the train model to increase the mass. Hey, I know. Let's use erasers. We can change the mass of our train model by adding different numbers of erasers to the model. We will keep everything else the same as in our last train model investigation. Before we begin our investigation, let's make a prediction. When we increase the mass of the train model, do you think the train model will go faster or slower? Do you think a train model with less mass will move faster? Maybe. Objects with less mass are easier to push. And when we add more erasers to the train model, do you think it will move slower because objects with more mass are harder to push? Let's investigate to find out. We should start by testing the empty train model. But wait, we've already tested an empty train model with 4 newtons of force. So we can use the data from our last investigation. Great! Now we just need to complete our investigation with 3 erasers and 5 erasers. Let's watch the first trial with 3 erasers.
3, 2, 1, start.
Let's look at the stopwatch. Wow! The train model took 1 and 5900 seconds to cross the finish line. I think that number is greater than the numbers in any of our trials with an empty train model. Let's check. Our first trial with 3 erasers took longer than any of the trials with 0 erasers. I conducted 4 more trials with 3 erasers. Let's look at the rest of the data set. Can you figure out what the middle number is? 1 and 5900 seconds, right? Now let's test the train model by using 5 erasers. Before we watch the video clip, let's make a prediction. Do you think the train model will move faster or slower with 5 erasers than it did with 3 erasers? Well, our original prediction was that if we add more mass to the train model, it will move slower. So do you think the train model will move slower with 5 erasers than it did with 3 erasers? Let's find out.
3, 2, 1, start.
It was hard for me to tell from the video clip. I performed 4 more trials with 5 erasers. Let's look at the data. Wow, look at that. The data support our prediction. The train model took longer to cross the finish line in every trial with 5 erasers than it did in any of our other trials. Can you figure out the middle number for this data set? 2 and 100 seconds. Let's analyze our data. What happens to the speed of the train model when we add more mass? When we added erasers, the train moved slower. And the empty train was faster than the train carrying 5 erasers. What do your observations tell you about how mass affects an object's speed? I think objects with more mass travel slower than objects with less mass when the same force is used. Do you agree? That means when an object has more mass, its speed gets slower. Let's add this information to our class chart. Now we know an object with more mass starts moving more slowly than an object with less mass does. One of your tasks after this lesson will be to update the class chart. Our investigation with our train model taught us a lot, but it had some limitations. Where does the force that moves the train model come from? The force comes from the spring scale, right? And where do you think the force that moves a light rail train comes from? Do you think the engine or motor of the light rail train is involved? Look at this diagram. Light rail trains, such as DART rail trains, have electric motors. The force that moves the train comes from a motor. The motor gears turn the axle gears. The axle gears connect to the axle, and the axle turns the train's wheels. And what happens after the motor gears connect to axle gears to turn the train wheels? The wheels push on the rails and move the train forward. Engineers design light rail train motors. How do they figure out how much force is needed to move the trains? Well, they consider both the mass of trains and the expected number of passengers. Wow, that's so interesting. We've been working to answer the question, how do light rail trains start moving? Do you think we know the answer now? I do. A train starts moving when a force is applied to the train. The force causes the gears and axles to turn and move the wheels of the train. Let's add what we've learned to our model. We learned that the motor turns gears on the train's axle. Do you remember where the axles are? Between the wheels, right. I think we should put our motor and gears and axle right here, close to the wheel. Now let's add labels. Great. We've also learned that people use transit systems, such as light rail trains, to move from place to place. Let's add some people to our model. We can add a driver and lots of passengers. But hey, won't that increase the mass of the train? Yes, if the train's mass increases, we need to increase the push force, right? Let's update our push force label to say, stronger push force for a full train. Wow, we added a lot of information to our model. Now let's update our explanation. We know that a motor is involved in moving the train forward. Let's start our explanation differently. We can say, a motor turns gears that connect to the axle. The axle turns wheels that push back against the rails. The train starts to move forward because the force pushing the train is stronger than the backward force of friction. Stronger forces can make the train move faster. A train full of passengers has more mass and starts moving more slowly than an empty train with less mass does. This looks great. One of your tasks after this lesson will be to update the class model and class model explanation. We learned so much about how light rails start moving, but I still have questions about DART rail. Do you? Well, when the DART rail starts moving, it doesn't go on and on forever, right? We've seen it slow down and stop. But how does the DART rail do this? In our next lesson, we will explore the question, how do light rail trains slow down and stop moving? Let's review your tasks for today. First, update the class chart. Second, update the class model and class model explanation.